Okay, welcome everybody to episode 2 of Games with Go. And we're going to do our first programming today. So, we're going to open up the folder we made last time, wherever you put your Golang folder. So for me, that's in users Go, source, GitHub, and then my name. Go ahead and select the folder you put inside the Go path. That's your name. And we'll be able to see the hello world from last time. And we're going to start a new folder today to go over variables, loops, and conditionals. So you can make a new folder if you click outside here. Let's see. How do we do a new high-level folder? I guess file. Well, here, we'll do it the command prompt way. So if you bring over your command prompt with Control tilde, just do make dir. We're going to call this basics because we're going to go over the basics. And then cd into basics, so the command prompt will be there when we need it. And then how can we refresh this? There we go. All right, let's make a new file. You can click that icon, call it basics.go. All right, so last time we made a hello world program, but I didn't talk about how that worked at all. So we'll go over that now. The first thing any Go file needs is a package name. And you declare that by saying package and then giving it any name you want. Except if your file is going to be an executable file, something that you compile and then run, as opposed to a library, which some other executable file would use, you need to call it main. So main is a special keyword that says this package is going to be an executable. And then when a package main executes, it's going to start at a function called main. So normally you can call functions whatever you want, but main is a reserved word. That means that when you run your program, it's going to start right here at the main function. So you always need at least this much to have a valid Go program. And this would compile. You notice if we save it with Control S, we don't get any errors, but it wouldn't do anything because it doesn't do anything. Now the next thing we had in Hello World was an import statement. We said import FMT, which stands for format. And that is a library, or it's basically another package, just like this is a package, but it's one built into the Go language. And it lets you do things like print to the console. And so we use that format package by using its name, hitting dot. And then here, if you have the Go plugin in your editor, it'll show you all the functions you have available to you in that package. So we have these things: scan, sprint, printf, printline. And we used printline to say hello world. And so that's it. That's all that is going on with hello world. You have a main function, which is where things start. You use the format package to print to the console. So now we're going to talk about variables. Variables are where you can store data, and every variable has to have a name and a type. Go is a statically typed language, which means all of your variables have types that are decided ahead of time. Some languages like JavaScript will decide the types at runtime. Things still have types eventually, but it's not, you don't have to declare them ahead of time. In Go, you do. So the way that works is you start with the keyword var to indicate you're declaring a variable. Then you pick your name. I will just call it A. And then you declare your type. So we're going to start with the type int, which is short for integer. And that basically means whole numbers. So numbers like 0, 1, 2. It can be negatives, it can be negative, 1, 2, and so on. You cannot put decimals into an integer. That doesn't work. And This here is a comment, so you can do slash slash starts a comment. This will just be ignored by the compiler, so you can use it to leave notes for yourself. This is the same syntax as in many other languages for comments. All right, so you notice we'll have an error here. If we hover over it, it'll tell us A is declared and not used. The Go compiler will not let you declare a variable that is never used. It'll be an error. And that just helps you clean up, if you've deleted the use of a variable but forgot to delete the declaration, compiler lets you know, so you fix it. So we got to use it. So let's use it down here. Let's print it. So the print line function is smart. It can take other kinds of types besides strings. So we can print the A as well. So let's see what we get. We're going to go run basics.go in the command prompt down here. And we see it says 0. So it turns out in Go, if you do not set a value for a variable, it will automatically assign it a 0 value, which for integers is 0. So that's easy. It should be noted that some languages don't do that. In C, it's up to the implementation, for instance. But in Go, you get a guarantee that if you declare a variable, it will be set to 0 unless you set it to something else. So as well as being declared, you can assign values to variables. And you do that with the equal sign. So we could say A equals 5. And then if we print that, now we see a 5. That makes plenty of sense. There's a shorter way to do this. You can just put the equals 5 up here. That is exactly equivalent as what we did before. It's just shorter to type. And you'll notice here it says, should omit type int from declaration. So what the Go plugin is telling us is that the Go compiler can infer the type of a variable sometimes. So in this case, if we left out the int, because we've just called this a 5 and not a 5.5 or otherwise annotated it, it will assume this is an int. So A will be an int, and it will work just like before. And if we hover over it, we see the Go plugin telling us it knows it's an int. So very good. And then you can shorten this even further. You can use this syntax. What this will do is assign and declare a variable at the same time. So it's exactly equivalent as what we did before. It's just less typing. It's just a shortcut built into the Go language so that you don't have to type var first. Same thing. Okay. Any questions so far? So int is not the only type that's built into the language. There are many. In fact, there is a whole bunch of different integer types. You can have, let's see, var a, int 8, var b, uint 8, var c, int 16, var d, uint 16, and so on and so on, all up to 32 and 64 as well. And what this is just different sizes of integers. So this is represented by 8 bits. So literally 1, 2, 3, 4, 5, 6, 7, 8 ones and zeros. This would be the number 0. That would be the number 1. That would be the number 2. And because there's only 8 bits, you only have room for certain sizes of numbers. For instance, this would be, I think, minus 127 to 128. Is that right? Let me check. Minus 127 to 127. If you try to assign values larger than that to an int 8, it will overflow, and we'll show what that does in a minute. When you have the u in front, that just means unsigned, and that means the numbers can only be positive. So this would be 0 to 255. You cannot assign, if you assign a negative number, it's going to overflow. So uints are unsigned and are only positive. And then int 16 is just twice as many bits, so you can represent much larger numbers, and so on for 32-bit and 64-bit ints. When you just use a regular int, this will be 32 bits on 32-bit machines, 64 bits on 64-bit machines. Why are we getting errors here? Oh, we don't need these colons. and they're all unused. That's fine for now. Okay, so why would you want to use this? If you knew that 32 bits was always going to be enough, you might want to use the int type because it will sort of use whatever hardware's default type is. Like you might get better performance if you just always use int. And it's just less to think about. So if you're not dealing with very, very large numbers, you might always want to use just default to using int if you don't want to think about exactly what type you want. Okay, someone in chat was asking about the colons, and that was just me making mistakes. All right. As well as integers, there are floating point values. So if you want to represent things like pi, you need to use floating points. And there's two types of floating point values. There is float 32, and there is float 64. And again, that's just bigger. 64 is just a bigger version, so you can represent more precise values or larger values with 64-bit floats than you can with 32-bit floats. Okay? So I'm going to make this a big comment. You can make multi-line comments with this syntax. / starts it, and / ends it. So everything between them will become a comment. All right, so you can't, Go does not do implicit type conversion. So implicit type conversion, many languages will let you say something like this. You can say var a int, well, let's just do the shortcut. So a is equal to 5, that's going to be an int. And we'll say b is equal to pi, approximately. What if we wanted to just say, what is a plus b, and print that? And we'll see here, we get an error, invalid operation a plus b, mismatched types. So in Go, you cannot mismatch types on accident. You have to explicitly tell the compiler that you want to convert one of the types to match the other. So we could do that by converting b to an int. And let's see, it's still unhappy with this. Closing brace. And then that'll run and say 8. So you'll notice when a floating point is converted to an integer, what happens is it's truncated. It's not rounded, it's truncated. So that's just going to end up being 3 when you cast it to an int. And then you could also instead cast a to a, let's see, does this go to a float? I don't remember if it defaults to float 64 or 32. Yeah, 64. So here, we've now converted a into a float, and so it can do a floating point addition. And you get the result. So you notice here we're using the plus operator. So there's a number of operators built into the language. You have the things you would expect, like plus, minus, division, and multiplication. And there are others as well, but we won't get into those yet. And one thing to keep in mind is that computers, when you use the types that are sort of built in to the hardware, they're not doing real math. And so I'll show you what I mean by that. Let's make var a uint 8, and we'll set it equal to 250. And we'll make var b, another uint 8, equal to 10. And we'll make a var to hold the result of adding these two numbers. Right? And that'll just start out as 0. And then we're going to say result equals a plus b. And let's print it and see what we get. So what we get is 4. 250 plus 10 is 4. So like I said, computers aren't doing real math unless you write a lot of code to actually do real math. With these primitive types, if you go beyond the maximum size they can handle, in this case, this is, right, can't be more than 255, it will overflow. And the behavior in Go that's defined for that is to, you basically wrap around. So if you had 255 exactly and added 1, it's going to wrap all the way back around to 0. And if we added 2, we would get 1. Nope, didn't save it. We get 1. Another example where math is not real is floating point, and this catches beginners out all the time, is with floating point values. So let's say that A is equal to 3.0 and B is equal to 2. Let's make this 2 and this 3. And then we'll say result is equal to A over B. And then we're going to do a special kind of print function so that we can see all of the decimal points of our floating point value. And that looks like this. So printf lets us specify formatting options on the things we print. I'm going to call this R, because result is actually a reserved keyword, so I'll avoid some confusion. All right. So R is now equal to A divided by B, which we would expect a certain exact value if it were real math. And what I'm saying here is to print out all the decimal places of this floating point value that we can. So let's see what we get with 2 divided by 3 in floating point. So you'll see down here, if we did real math, we would actually get a fraction, or 0.6 repeating. But what we get is 0.66666, and then it all falls apart, and we just get junk here. The lesson here is that floating point is an approximation. The computer only has so many bits to work with, and so you're not going to get exact answers. And in many cases, the answers will always be very close, like this is. This would probably be close enough for most things you would use for dividing 2 and 3. But there can be cases if you're doing math over and over, this error can build up, and sometimes it can be unexpectedly very, very wrong. So when you use floating point, you always have to be aware of that and pay attention to what you're doing. All right. As well as the numeric types, there are a few others. So I'll leave this here as an example of math is not real. And by the way, there are languages that have built-in like arbitrary precision math and big integer math, and there are libraries for doing that kind of math in every language. But these are the built-in primitive types. These things are very fast. If you use libraries that do arbitrary precision math or can handle like infinitely large numbers, they're hundreds of times slower because the hardware doesn't have instructions to run those things in one step, whereas you can divide a floating point value by another in a single instruction. All right, operators, variables. Okay, a couple other variable types. There are Booleans. So you can have things T or F is equal to true. So that's an example of a Boolean value. And you can print line that. Right, so these can only be true or false. And behind the scenes, these are implemented with a byte usually, or you can think of them as an int 8. They still take up 8 bits, even though they can only be true or false. So don't be tempted to try to like save space by using a Boolean instead of an int, if an int would make more sense. But they make your code much more understandable for times when you really want something that's just true or false. You can use a Boolean. And let's see. If you had to declare that explicitly, I believe it is bool. Yeah. And it's here, it's telling us it can infer it. But bool is the type. And then there is, make this a comment now. There are also strings built in. So you can say hello world. And strings, you just use double quotes to indicate that they're a string. And then, of course, you can format.println those as well. And we get hello world. So those are some of the common types that are built in. And you can also build your own types, which we'll show that later, not today. But you can make your own types of any complexity that you want. Okay, so I think that wraps it up for variables. Oh, it is episode 2, and I will update the title. Let me go do that now. Thank you, chat. Edit info. All right, title's updated. Okay, I think next we'll show loops. If you're used to other languages, you might be used to seeing for loops, while loops, do while loops, things like that. Go condenses these all into just for loops. So we'll do the first example, which is easy to understand, the infinite loop. If you want to do an infinite loop in Go, you just type for, do the curly braces, and then put whatever you want inside. And when this runs, it's going to start here, it's going to go here, it's going to go here, then go back up, around and around, forever. So let's try running it. Sure enough, it's printing hello world forever. So loops are handy when you want to do things lots of times. You wouldn't want to have to, for instance, type hello world infinity times if you wanted to print hello world all day. So instead, you can just use an infinite loop. But you don't often really want to do infinite loops. Usually you want to do things a certain number of times. Oh yeah, if you want to hit Control C to break out of your infinite loop if you want to kill it, and you probably do. So let's try this. Let's set a variable I is equal to 0. And we're going to do the equivalent of a while loop in Go. So you can say for, and then give it some expression, any expression you want that resolves to a Boolean. And so here we're going to use a comparison operator. We're going to say for I is less than 10. And then we're going to print line hello world. And let's also just print out I so we can see what's happening. Typo there. Okay. So what we've done here is we've created a new variable that's an integer called I, and we've set it equal to 0. And then we said for I is less than 10, print line hello world. And then we're going to add 1 to I each time we go through the loop. So what should happen here is we should see hello world printed 10 times along with the current state of I, and then the loop should exit once I is no longer less than 10. And so there we go. See hello world 0, 1, 2, 3, 4, and so on. And once I was equal to 10, then it was not less. So this was resolved to be false, and the loop exits. So that's equivalent to a while loop in other languages. And then this is like a really common pattern here. This pattern where you start from 0 and you go to some endpoint and you add 1 each time to the number that you're counting. And so the normal way you would do this is you can do this all in one step. Let me just label this. This is sort of the normal for loop syntax people are used to. You can say for I is equal to 0, semicolon. I is less than 10, semicolon. I equals I plus 1. And then you can do the same thing we did here, print out hello world and I, and run it. You get exactly the same result. These two things are equivalent, just as just a shorter way of typing that out. And this is, again, something you'll see all the time when people are going through lists of values or counting up. You'll see for loops using this pattern. And one other shortcut you can take, anytime you want to add just one to something, there is a shorthand for it, I++. There's also an I minus minus to subtract by 1. So you can shorten it down to that. Again, it runs the same. Once it's compiled, there's no difference between the two variations we've done here, probably. It's just so you have less typing to do. That's the only thing it's there for. All right, so that's loops. The last step we've got is conditionals, or people call this flow control sometimes. So programs have the ability to do one thing or the other depending on the state of the program. So let's keep it simple at first. Let's say that test is equal to true. So test is a Boolean. And we want to print hello world if test is true, and goodbye world. Oh, someone asks which variation of for loop I recommend. It just depends what you're doing. I think it'll kind of be obvious when you start writing real programs what you need at the time. When we're done here with the conditionals, we're gonna do a short game, and we're gonna use one of the loops. We'll actually end up using this type. We're gonna use an infinite loop, and I'll show you how to make it not really infinite. But yeah, any time that you're kind of starting at 0 and just counting up, you'll tend to use this format. All right, so we want to do one thing if test is true and something else if it isn't. So we can just say if test. We'll say print line hello world, and then you can say else format.println goodbye. Okay, run that, and we see hello world because test was true. And since it was not, since it wasn't false, this whole else block is skipped. And if we switch the value, we see goodbye. All right, that's pretty simple. You can also rewrite this like this: if not test, print goodbye. Okay, so test was false. So if test is false, so we don't do it. Then we say if not test, so not of test is true, so we print goodbye. And yeah, the exclamation point is a special reserved character that means not. It's like saying if not. Okay, but whenever you have sort of an either or situation, the normal way to do it is with if else. All right, let's make it a little more complicated. Let's say x is equal to 5. So now x is equal to an integer. So now you can do things like this. You can say if x is greater than 5, do one thing. Otherwise, do the other thing. Why is this not happy? Okay. So now we run it, and we see goodbye because x is not greater than 5, so it went to the else. Now let's make it more complicated again. Let's say else if x is less than 5, print goodbye, else it is 5. All right, so now we have an if and else. Sorry, everybody. My headset turns off if no sounds play for a while. Okay, so we have else, if, else if, and then else. So we run it, and we see that it's 5 because it's exactly 5. If we made it 1, we'll see goodbye because it's less than 5. So you can chain these together as many as you want. You can do else if, else if, else if, else if, else if, as many different conditions as you want. So this is kind of how you can make decisions in your program's logic. All right. Any questions so far? Okay. Let's move on and make our first simple game. So I'm going to make a new folder called guess. And I'll make a new file in there called guess.go. And then as usual, we're going to start out with the package main. And we're going to import a few things this time, not just format. Okay, so we're going to import format. And we're going to import some things that let us get input from the user. Now, Go has a nice shorthand so that you do not have to type import over and over and over when you're importing multiple things. You can just go like this. Wrap it in parens. Oh. Okay, so that the Go plugin will try to automatically do your imports for you when you save. So I'm not going to save yet. All right, and we're going to need a main function, which is where everything starts. And we need to get input from the user, because what we're going to do is we're actually going to make the computer play a game against us. We're going to make the computer play guess the number against us. So the computer is going to ask us to think of a number, and the computer is going to try to guess it. And then we're going to tell the computer if it's too high or too low, or if it got it, and the computer will keep guessing and see if it can find the number we're thinking of. So we're going to make it play against us. So the computer is going to need input from us, and Go has some built-in libraries to do that. So we need to make something called a scanner, which is what will read input from the console. So we're going to make a new variable, scanner, and we're going to declare it and set it equal to buffio.newScanner and then os.stdin. All right, so that's a lot of mess. What all is it doing? So buffio is a package built into the core Golang libraries that can read things from input sources. And we tell it we want to make a new one. And then by passing os.standardin, we're telling it that the input source we want to read from is when people type in a console, like down here. That is what stdin means. Okay. So now we're going to print out some stuff for the start of the game. We're going to say format.println. Please think of a number between 1 and 100. And then we'll say press enter when ready. All right, that's our fancy load screen. And then we need to wait for the user to press enter. And we can do that by telling the scanner to scan. So what that means is the scanner is going to sit there and wait until it gets input from the console, which it senses input when you press enter. All right. Now we're going to do an infinite loop because we want the computer to keep guessing what our number is until it gets it right. And we also need an initial guess. So let's make a new integer guess, and we'll just set it equal to 50, right in the middle of 1 and 100, because that seems like a good place to start. Okay, so then we'll say format.println. We're going to say what the computer's guess is. We'll say I guess the number is, and then guess. Right, so the first time through, it's going to print 50. But now we need to get input from the user about whether that's too high, too low, or exactly right. So we'll ask, we'll say, is that A, too high, B, too low, or C, correct? And then we will scanner.scan again to get input from the user. But this time we're actually going to look at what the response was. So we'll set the response, make a new variable, and set it equal to the result of scanner.text. So what scanner.text does is whatever input came from the scanner the last time you scanned it, scanner.text will give that back to you as a string. All right, so response will be a string with whatever the user typed. So now we can combine our infinite loop with a conditional, which we learned earlier. We can say if response equals A, and notice here that we have two equals. Many languages are like this. Because we've reserved a single equals to set variables equal to things, we have to use two equals to ask if two things are the same, right? So to test for equality, it's two equals. To set a value equal to something is one equal. That is very confusing to beginners. All right, so there's three possibilities. Response can be equal to A, or B, or C. And if you want to be good about error checking, the response could actually be something else if the user typed in something bad. So we should probably handle that too. So we'll have if A, else if B, else if C, and else to cover all of our bases. All right, so if our guess was too high, we need to adjust our guess downwards. So the most naive way we could do that, a somewhat stupid way, is to just subtract 1 from our guess. So I'll do that with the shorthand minus minus. And if our guess was too low, we need to adjust our guess upwards. And again, we could naively just increase our guess by 1. And if our result was correct, we can just declare that we won. And if the response from the user was no good, we can just say invalid response, try again. Easy enough. Okay? So when we won, if we do win, we don't want to keep looping forever because we've already won the game. So there's a special reserved word called break. And what break will do is exit whatever loop you are currently in. So this is the only way out of the loop as if you guess correctly. So the for loop will keep going, going, going until response equals C, print I won, and then break out of it. And when it breaks out of it, execution returns to right here. All right. So let's give the extremely naive number guesser a try. Oh, wrong folder. So guess, go run, guess.go. All right. All right, chat. Please think of a number between 1 and 10. Somebody type something, and we'll play. Anybody, any number. All right, 42. I pressed enter. Okay. I guess the number is 50. That is too high, so I'll hit A. I guess the number is 49. Still too high. Still too high, still too high, still too high, still too high. Almost there. 42. That's correct. I'll respond with a C, hit enter. There we go. All right, so it works, but it's really dumb, right? So we can actually express how dumb the program is in a kind of rigorous way. We can call this 1 through 100. That's kind of our solution space, right? That's the size of the space we're searching. 100 different items, basically, right? And on average, if we guess random numbers, or if we think of random numbers, our program's going to have to kind of try at least half of them, right? Because it's only going one at a time. So there's a concept of computer science called big O notation, which lets you express how slow an algorithm is, or how much space an algorithm is in terms of the size of the input. So in this case, our input size is 100. And in order for our computer to guess, it's going to have to guess about 100 over 2 guesses before it gets to the answer, because it's starting in the middle and then just counting up or down by 1. And when you do big O notation, you basically ignore constant factors like this. Like if you have to do 100 divided by 2 or 100 times 2 iterations to get the answer, it doesn't matter. It's still the same thing. So if we say that n equals our 1 to 100, our solution space, the big O notation of this algorithm is O of n, right? Like if we have a million, if we have a number between 1 and a million to guess, we're going to have to guess, almost a million times to get the answer. If we double the space of numbers to search, this algorithm will have to double how much work it does as well. So we can say it's linear, right? The runtime of this is linear with respect to the size of the solution space we give it. And linear is often really good, but we can do much better than that. So does anyone in chat want to suggest a better strategy than just increasing our guess by 1? Or subtracting our guess by 1? All right, no takers. So what we're going to do is something called a binary search, which is kind of a fancy sounding computer science term, but it's really pretty simple. So let's say that this is our search space. We've got a line going from here to here, where this is 1 and this is 100. I apologize for my handwriting. I'm terrible at this. All right, so our initial guess currently is in the middle, and that's actually a good idea. So we're guessing 50. So if our guess is too high, rather than just searching a little over this way, what we actually would like to do is search halfway between our current guess and the previous lower bound. So that would be 25. So let's say we guess 25 and then our guess is now too low. Then again, we want to go halfway in between our current guess and the current upper bound, which is 50. Right? So you just keep going like this, halfway, halfway, halfway. And it turns out you get to the answer. That is the optimum way to get to the answer. You'll get there very fast. And in fact, if you express the runtime in terms of the size of the input, so if the size of the input is n, then binary search will find the answer in the log, I think the natural log, but basically log of n steps. Right? So if you have a million things to search through, it'll still find it pretty fast with the binary search, because you're cutting the search space in half each time you guess. And another thing we should do is we should avoid magic numbers. So this is just a guideline when you're programming to avoid these. Anytime you see just numbers floating out like this 50 or this 1 in 100, you should try to get rid of them and save them as constants or as variables somewhere. So we'll do that like this. We'll say the lower bound is 1, and the high bound is 100. And then here we'll actually print those out. Like this. And so what this does, this helps us avoid mistakes, right? Like we don't have to remember 1 in 100 everywhere below in our program. We're always just going to refer to the low and the high variables, right? So we're always going to be correct. We're going to be correct with the things we print out, and we'll be correct here with our logic. That is the motivation of avoiding magic numbers. So our guess now, we're going to bring it inside the loop. And we're going to say that our guess is equal to the middle of the low and high ranges. So we'll say that our guess is equal to low plus high divided by 2, which will always put our guess right in the middle of low and high. And then if our guess is too high, what we do is we adjust the upper bound of the range that we're searching. So we'll say high is equal to the guess minus 1, right? Because we know the guess was too high, so the highest that the correct number could possibly be is 1 less. And then if our guess was too low, we adjust the lower bound to be our guess plus 1. And that's all we have to do. We will now be jumping to the middle of our search space each time through the loop and adjusting our search space based on whether the guess was too high or too low. And that will be doing a binary search, which brings us from a linear algorithm to a log algorithm, so that we can handle even if we made this 1,000, we could get the answer really fast. So let's try it. Chat, you want to think of a new number? Anything at all, chat? 11. 11, excellent. All right. We guessed 50, that is too high. We guessed 25, that is also too high. 12, too high. 6, too low. 9, too low. 10, too low. And boom, we got it. All right. So now we have a optimum number guessing machine that can play the game as well as it can be played. All right. Does anyone have any questions about what we've done so far? Questions, comments, concerns? So I'm just going to label that with a comment. Okay, so what I'd like for you guys to do, it's always good if you're learning a new language or learning to program to practice on your own. So here's a few things sort of for homework. There will not be any grades, but I encourage you guys to play around. So one thing you can try, make the program, print out how many tries it took to win. All right, so once it wins, you'll need to print out how many tries it took to get there. Another thing you can do, currently this program has some flaws. It has some error conditions it doesn't handle, right? So guess number between 1 and 100, right? Let's see. Nope. Oh, okay. Yeah. So what if I was thinking of the number 200, and I go through this process, right? What's going to happen? Someone is asking about a delay between stuff on chat and stuff in the stream. And yes, I believe that is normal. There's like 3 or 4 seconds normally. I'll take a look at my settings afterwards, but I think that's just how it is. Okay. Um, yeah. So what if the person uh, giving the or thinking of the number was thinking of one outside of this range? Currently, the program would just it would get stuck on one number and keep guessing over and over because it wouldn't know what to do. So the program should be able to identify when that's happened, right? If the program's like search the entire space and the user keeps telling them they're wrong and it can't be wrong. So see if you can. See if you can tell the user is lying and just say, you're cheating and then quit or whatever you want to do. All right. First one's should be pretty easy to do. This one might be hard. I don't know. You guys can try it, and then next week we can talk about it, and you can show me kind of what your solutions were. All right. Any questions? Any thoughts? Okay. So Willie asks if Go supports inline if statements. So in some languages, you could do something like this. So it won't let you do it that way. Yeah, so Go requires that you have the curly braces. And I think it'll let you do it like this, but the sort of the the Go plugin that we uses Go format on the code automatically. So every time you save, it formats it the way Go format wants you to format things. And the Go community kind of wants everyone to use Go format. So I would stick to this. I know it is convenient in some languages to be able to have it all inline. Let me check real quick if there is like a different syntax for that, but I don't think so. Yeah, no, you can't do it. So the answer is no. All right, that is it for tonight. Um, the next stream is going to be on Sunday. Previously, the plan had been to do Saturdays, but I cannot do this Saturday, so we're going to do Sunday, 8 o'clock. And Sunday, we're going to learn more about functions, how to make our own functions. We're going to learn about pointers, and we're going to learn how to make our own types. And we're going to start on a simple text adventure. We'll see how far we get with functions, pointers, and types, but we should start some of our first text adventure. And pointers are pretty exciting. Java programmers hate them. They don't even know what they are, but we're going to learn. That'll be fun. All right, so I'll see you guys in a few days on Sunday. Thanks, everybody. Signing off.